Imagine this. You kick off an ambitious project with a whopping 120 lithium-ion cells, only to find yourself down to just 23. Welcome back to the thrilling journey of part 3 of this series. This twist became my reality in early May. My grand vision was to build a solar-powered lithium-ion battery pack, but after intense testing, I was left with a mere fraction of my original cells. It's worth mentioning that all 120 cells were salvaged from old laptop batteries. To appreciate the full scope of this adventure, I highly recommend checking out parts 1 and 2, which lay down all the background info you need. You can snag those links at the top right corner of your screen. In today's video, we're diving deep into building a DIY device that will measure the milliampere hour of those remaining 23 cells. First, I'll need to gather some budget-friendly items that are super accessible. Here's what I've got: a prototyping board, a USB doctor, a USB load resistor, a USB female connector, a TP4056, a single-cell battery holder, and a switch. But wait, this switch is way too big and clunky for what I need. A sleek push button would be much better, right? But then I realized I had grabbed the wrong type of push button. Plus, I added a few wires to the mix. Everything seemed set, but boy, did I quickly discover I had a lot more assembling ahead of me. Here's the kicker. The two must-have items if you're thinking of replicating this test for yourself are the USB load resistor and the USB doctor. The load resistor is critical for discharging the cells at either 1 amp or 2 amps, and the USB doctor, it's my secret weapon for capturing the vital milliampere hour readings as the cells discharge. You won't believe how perfectly this push button fit onto the prototyping board. It almost dazzled me into forgetting how it was supposed to work. My frustration led me to damage it. I was initially determined to steer clear of a reliable switch simply because it looked less appealing. I went through loads of push buttons, both 4-pin and 2-pin, but no luck. Stick around as I explain why those switches become crucial to the project. As I kept brainstorming the design, it hit me hard. I'd need this contraption to run non-stop for over 15 hours a day to test all 23 cells within a 72-hour window. This meant I required some upgrades. My original prototyping board was too small, so I lofted it up to a larger one to fit a 4-cell battery holder, a cooling fan, and a handy DC-to-DC voltage step-down module. After convincing myself I had all the pieces in place, it was time to dive into assembly mode. I started with the 2 battery holders since they take up most of the space. Then came the TP4056, the USB doctor, the USB load resistor, and 2 slide switches. Oh, and just pretend the black push button at the center isn't there. It's just a joke. But seriously, if you compare the slide switches and the push button, definitely the push button is well secured and looks more appealing. Considering the way I just mounted the slide switches, it makes them to be less appealing. Now, let's talk about managing the heat produced by the USB load resistor. At 2 amps, those resistors can deliver a first-degree burn in under 10 seconds. Why did I add a fan atop that load resistor? For 3 main reasons: to avoid accidental burns, to keep things looking sharp, and here's the brainy part: if I cool those resistors during testing, I might just extend the lifespan of this rig, especially since I glued everything together permanently. Looking back, that glue job might not have been the best idea, but by the end of this test, we'll find out if it pays off. To tackle the heat situation, I chose 1.5-inch screws to create just the right airflow beneath the USB resistor. These screws allow for bolting to increase the surface area for gluing the fan onto the prototyping board. Longtime followers know I love epoxy glue. Sure, some people aren't fans, but I find it effective in speedy bonding capabilities across different materials. Initially, everything was glued down with that epoxy, but spoiler alert, things evolved, as you'll soon see. However, I suspect the glue isn't strong enough to keep the battery holders secure since they snugly grip the cells. making it quite a challenge to pop one out. The adventure began with a crucial challenge: powering my fan with the right voltage. This little powerhouse needed 12 volts to perform its magic, and since I wanted it to run for an impressive 15 hours a day over 3 to 5 days, I had to get my 4 cells, capable of pumping out over 16 volts when fully charged, regulated. Running the fan on full voltage? Not a chance. It would barely last 10 hours. Enter the hero of our story, the DC to DC voltage step-down module. Before I got all hands-on and secured this module in place, I figured it was smart to adjust the voltage output first. The process was simple yet thrilling. I connected the positive and negative wires on the inlet side of the module, then grabbed my trusty multimeter to make sure everything was right on the other end. With the output set meticulously to 12 volts, I removed the push button and slotted the module into position. Now, onto the riveting soldering part. Full confession, my soldering skills leave much to be desired, and I'd rather not summon the keyboard warriors lurking in comments. So, let's just pretend my wiring looks flawless. Honestly, as long as it works when I flip the switches, that's all I care about at this stage. Speaking of the nitty-gritty, let's dive into how this contraption is supposed to operate. The single-cell battery holder holds the cell I need to test, which is then connected to the TP4056 module through the B positive and B negative terminals to fully charge the cell before diving into testing. Then I have 2 wires connected to the out positive and out negative that are then connected to the positive and negative terminals of the USB female connector. It has 4 pins, but I only need the positive and negative ones. Thank goodness for multimeters to keep me on track. Now here's where it gets really exciting. The USB female connector links to the USB doctor, where I'll capture the readings from each cell. But to truly discover the milliampere hour of each cell, I need to discharge it using the USB load resistor. Oh, and I'm cranking it up to the 2 amp setting, meaning there's bound to be some serious heat. Enter the fan, just a small hiccup. When I connect the 4 cells in series, they crank out 16 volts when charged. Way too much for the fan. Thus I need to dial it back to 12 volts with my trusty module before powering up the fan. One more thing, I threw in 2 switches, one to fire up the fan and the other for the USB doctor. If wiring up switches seems tricky, just hit up YouTube for some expert advice. Then, inspiration struck. I remembered a 3S battery pack I had resurrected a few months ago, and each cell boasting a hefty 5,000 milliampere hours. This felt like the perfect moment to see if I could reach those numbers. Yes, I know it's a 3S pack. With cells in series, the milliampere hours stay the same while the voltage triples, but I was left pondering whether the USB doctor could handle the full 12 volts. I scoured online forums and found conflicting information. Some sellers claimed it could only handle up to 9 volts, while others stated a maximum of 20. It felt like walking a tightrope, unsure if I was about to ruin my device, which had parts glued onto the board. After carefully connecting the 12-volt LiPo battery, anticipation buzzed through me. I hesitated for a moment. Should I take the plunge and power it on? Curiosity won out and I flipped the switch. Nothing happened. Panic set in as I debated whether I made a huge mistake. Then I had a closer look, realizing the 12 volts had to go through the TP4056, which was only rated for 5 volts. Yikes. This led me to check the voltage readings on the pins connected to the USB doctor, and to my immense relief, my multimeter read 0 volts. That meant the TP4056 was likely cooked, an easy fix compared to a complete failure. Once I removed it and connected the battery directly to the USB doctor, it sprang to life. But the twists didn't end there. While testing the 3S pack, I set the USB load resistor to 2 amps, but lo and behold, the USB doctor displayed more than 2 amps being drawn. Instead of scaling back to 1 amp, I ignored it, and for a moment everything worked smoothly, until I decided to switch off the fan to check how hot the resistors were using my finger. First, I burned my finger, and suddenly, smoke began to waft from the USB load resistor. I quickly disconnected everything and let it cool before trying again. Talk about a close call. If you're testing batteries over 5 volts, skip adding the TP4056 altogether. One thing I learned through this exhilarating journey is that the USB doctor will stay on as long as it receives more than 3.2 volts, which lets the resistor keep the discharge going. I attached a multimeter to keep a vigilant eye on the pack, as the minimum safe voltage for a 3S pack is 9.6 volts. I nearly made a careless mistake by leaving it unattended and pushing the voltage to dangerous levels. In the end, I concluded this setup is not the best for testing a pack of cells. It truly shines when checking individual cells. Before diving into the testing frenzy, I had to make sure the USB doctor's switch was off. Let me tell you, I nearly lost it when I accidentally inserted the battery wrongly and sent the USB doctor into a frenzy. I was so frustrated that I didn't even capture that moment on camera. If you find yourself in the same boat, comment below, and I'll share my tips on restoring the USB doctor to its former glory. So, to kick off the epic testing saga, I needed to charge each cell fully first. The moment those indicators on the TP4056 shifted from red to blue, it signaled that the cell was ready for action. I switched on the USB doctor and flipped the fan on, but then catastrophe struck. I made a blunder that forced me to redo the tests on all 23 cells. Here's the scoop. I was too eager and assumed the test was complete when the LCD on the USB doctor turned off. Except when I checked each cell's voltage, they all showed above 3.2 volts, indicating I had stopped the test too early and missed vital results. What a roller coaster. Time to reset and dive back in. So this is what I did to get accurate results. I decided to add a DC digital voltmeter to the mix. My first installation attempt, though, became a hilarious blunder. I had it set up wrong and the display was dim as a nightlight. To correct the dimness, I supplied it with 12 volts from the 4 cells powering the fan, and at this point I was glad for previously adding the fan. Now the 16 volts had one more device to power. However, the challenge emerged when it came to powering the voltmeter separately, as it only had 3 wires. After a bit of head scratching, I finally cracked the code. I brought the voltmeter on board for 2 key reasons. The voltage readings from the USB doctor were wildly inaccurate, and whenever the USB doctor shut down, I was left in the dark about when the cells were fully discharged. Waiting for the LED light on the USB load resistor to turn off and the voltmeter to stabilize became my new pastime. Even when the USB doctor went dark, it continued gathering readings quietly in the background, causing the load resistor to flicker on and off. No wonder the voltmeter showed fluctuating voltage. When I inserted a fully charged cell and cranked the USB load resistor up to 2 amps, I felt like a genius. This saved me precious time compared to testing at just 1 amp. But here's the kicker. To my surprise, each cell was showing only 2.88 volts. Now I know that lithium-ion batteries can dip as low as 2.5 volts. But a battery management system typically cuts off between 2.5 and 2.9 volts. That means the readings I recorded were surprisingly better compared to the previous results. Wow, we've reached an exciting milestone with this device. I've really pushed it to the max, even adding some foam to jazz up the look and conceal those unsightly wires. But I want to hear from you. If you think there's something I might have missed or could enhance, drop a comment below. As we gear up for part 4, get ready to dive into the fascinating process of arranging these 23 cells, each with its own unique capacity and internal resistance, to create an incredible 12-volt battery pack. Here's a pro tip. When connecting cells in series, they should ideally have the same capacity, and those in parallel need to match in voltage and internal resistance. However, cells in parallel should have the same internal resistance for optimal performance. So, unleash your thoughts and recommendations in the comments. Don't forget to hit that subscribe button so you can stay updated on all the thrilling developments in part 4. Your support means the world to me, and I can't thank you enough for watching until the end.